Well, so today we have come to the tutorial after the 4th week. So, you are already halfway through the thermodynamics course. I believe you must have faced quite a number of doubts, and we have also got some very interesting clarification and doubts and questions from your side. We welcome much more questions on this. In fact, we would also welcome suggestions from you regarding explaining once more some portions which were not very clear, or maybe certain portions which you think had become more difficult and you would like to have like me to explain it once more. It will be good if you can put up all these suggestions on the portal. We will try to accommodate them as much as possible. Now, coming to the tutorial after the end of the 4th week, means we are already halfway through, and this is the tutorial for particularly pertaining to the next week. So, in this particular, the first problem is that let us see this problem, how do we handle this particular problem. What does it say? It says that liquid mercury boils at about 357 degrees centigrade. So, therefore, the problem 1, the boiling point of mercury, that is given as 357 degrees centigrade. Heat of vaporization is also given in calories per gram, mind it. So, therefore, it is not, it just note that this particular heat of vaporization which is given, this is given as the specific heat of specific latent heat of vaporization and not the molar latent heat. So, therefore, you have to keep it in mind that you are going to convert this to the molar latent heat of vaporization by multiplying it with the molecular weight of mercury, which is 201, and then it is given, it is required that the pressure which is required to distill mercury at 150 degrees centigrade. So, therefore, we know that at the boiling point of mercury, naturally it is going to have the saturated vapor pressure, right. So, therefore, at the P at this particular boiling point, this is nothing but equal to 760 millimeters mercury, and they want to distill mercury not at the boiling point, but at 150 degrees centigrade. So, therefore, T2, that is 150 degrees centigrade, and they would like to find out what is the approximate pressure required for this particular distillation. Now, you know that from the data which is given, you are given the boiling point, the corresponding saturation vapor pressure which is known to you, the latent heat of vaporization is given. If you assume that the latent heat of vaporization does not change from 150 degrees centigrade to 357 degrees centigrade, which is definitely, as we have already discussed, is quite a drastic assumption, but nevertheless we make this assumption to for simpler calculations, then in that case we find that the Clausius-Clapeyron equation can be quite suitable for it. What is the Clausius-Clapeyron equation? Let us recall. I had already discussed the Clausius-Clapeyron equation in the class. It was ln P2 by P1 equals to delta H vaporization by R 1 by T1 minus 1 by T2, is not it? So, therefore, if we use this, we find that we are required to find out P2, we know P1, right. Delta H vaporization, this has to be 68 into 201, and this is given in calories. So, therefore, the corresponding R also has to be taken in calories. So, therefore, this is 2, and 1 by T1 is 1 by 373 minus 1 by 630, right. So, therefore, if you solve this out, then what do you find? On solving this out, we find that we get P2 as 0.425 millimeters mercury. So, therefore, we find that this is the required pressure which is required to distill mercury at 150 degrees centigrade. This was quite a direct application of Clausius-Clapeyron equation, and let me tell you that you will be given some such direct applications of Clausius-Clapeyron equation in your assignments, and then possibly you will be evaluated also on the basis of these particular problems which are done in the class. I would like to mention that whatever evaluation process we take up, that is at the final semester exam or this final test that we take, more or less you will be dealing with whatever problems have been done in the class, the problems or the questions which are asked in the assignments. One more thing also I would like to tell you, that in the course of phase equilibrium thermodynamics for the last 4 weeks, you must have faced problems because you had to deal with a large number of formulae for estimation of properties and maybe several gas laws and several other equations. Now, we would be you will be required definitely to remember certain simple equations. For example, Clausius-Clapeyron equation you are supposed to remember, or it is not very difficult to derive it. Ideal gas equation, van der Waals equation you have been doing for a very long time. I suppose you already know these equations by heart, but all the difficult equations, say Maxwell's equations and several such equations, they will be posted before your test, and you can refer to those particular equations when during your test season. But it is not a bad practice to remember some of these equations for your future usage of thermodynamics, right. So, therefore, this was one particular application of Clausius-Clapeyron equation. Now, let us go to the next problem, a slightly more involved problem. What does it tell you? It tells you that water boils at 95 degrees centigrade in a particular hill station, right. We know that at the mean sea level water boils at 100 degrees centigrade. So, therefore, definitely the pressure on the top of the hill station is quite high as compared to the, it is quite low as compared to the pressure at the sea level, right. So, therefore, we know that at the sea level the pressure, the water, the boiling point, this is 100 degrees centigrade, and here the boiling point is 95 degrees centigrade. Why does this happen? Why is the boiling point difference? Naturally, because the pressure here has to be lower as compared to the pressure here. What makes the difference in pressure between the two places? It is naturally the difference in height between the two places. So, definitely between P1 and P2 there is a difference in height which brings about the difference in pressure, isn't it? So, therefore, this arises due to rho g h of the air column between the two, isn't it? So, therefore, from here we know that P2 minus P1 into A should definitely be equal to rho g h, right. So, therefore, due to this particular altitude difference there is a pressure difference which brings about the difference in the boiling points, and the question which is there is you are asked to estimate the approximate altitude under two conditions. What are the two conditions? First condition is atmosphere is isothermal. What does it imply? It implies that in the atmosphere PV equals to constant, or in other words, where V is this molar volume, or in other words your P2V2 at the altitude is equal to say P1V1 at the sea level. So, this one information is given. Possibly if we are going to use this information in order to express P2 in terms of P1 and then relate this particular equation from the basic force balance equation to find out H. This is problem 1, and the problem 2 is to repeat the whole thing if the atmosphere is adiabatic. Let us deal with problem 2 part A first and then we go to part B, right. So, here again use the same equation, ln P2 by P1, this is equal to delta H vaporization by R. I had already written it down earlier, 1 by T1 minus 1 by T2, fine. Now, here we know everything except P2, this is the only unknown that we have. You find other than that we know everything. What is P1 equals to? P1 is, and this P1 it is the atmospheric pressure. So, therefore, from here we know, and delta H vaporization, it is also given, it is given as 2256.94. In this case, just note that it is given in kilojoules per kg, right. So, it is better you convert it to joules, because we know R in terms of joules. So, therefore, this becomes into 10 to the power 3 joules per kg, right. So, therefore, this is 2256.96 into 10 to the power 3 joules per kg. Accordingly, your R, this is going to be 8.314. Again, in this case, you note that the latent heat of vaporization is the specific latent heat, it is not the molar latent heat. But in this case, you know that it is the substance or the fluid in between, it is air. So, therefore, what do? We simply multiply it with the molecular weight, the average molecular weight we assume, and from here I am just substituting T1 and T2 minus 1 by 368.15. Just note certain things when you are doing these problems. Firstly, T1 and T2, even when they are given in degree centigrade, they have to be converted to Kelvin, the absolute scale temperature. Next thing is, please note the unit in which delta H vaporization is expressed. If it is expressed as per kg, you are required to convert it to per mole. If it is, and also note the unit in which delta H vaporization is expressed, you are required to express R also in the same units, right. So, from here you know that ln P2 by P1, this is equals to minus 0.1778, right. What are you required to find out? You are required to find out the height difference when you know the ratio of the pressures or the pressure difference between the two, right. So, you need one more equation to relate the pressure difference to the altitude of that particular place. From physics, we know how we are supposed to do these. We take an infinitesimal volume element, say, and from the infinitesimal volume element, this is say the infinitesimal volume element, right. And in this infinitesimal volume element, the cross sectional area is say A, the small height is say dH. Here the pressure, suppose it is say P plus dP into A, here the pressure is P into A, and this pressure is acting here, and we find that the weight of the fluid which is acting downwards, what is it? It is A dH, the volume, into divided by the specific volume into G, right. So, therefore, for this particular volume we know that since there is no acceleration, so from force balance what we get? From force balance we get, this is going to be P plus dP A minus P into A. This is equals to A G dH by V, or in other words, it is better you write it down in this way, this is equal to 0, isn't it. So, P plus dP into A minus PA plus this is the pressure force and this is the gravitational force, this equals to 0. From where we get dP is nothing but equal to minus G dH by V. Please note that V is nothing but the specific volume, right. Now, for isothermal conditions, what do we know? We know that, as I have told you, P2 V2 equals to P1 V1, where P1 V1 refers to this, to the sea level, this refers to the sea level, and this refers to the height above the altitude. Agreed? So, therefore, can we not write down this particular equation, say equation A, if we can substitute dP, we find that this equation dP, this gives you as, this is G dH P by, or rather G dH P2 by P1 V1, isn't it? From where we find that, sorry, this is P, L or dP by P, this is nothing but equal to minus GdH by P1 V1 integral from 0 to h, when this integral extends from P1 at the sea level to P2 at the altitude h, right. So, from here what do we get? We get ln P2 by P1, this is equals to minus G by P1 V1 into h, agreed. And we know that P1 V1, since for this particular case we can easily express it as G by R T1, the temperature here, into M into H, where we know what is M. M is nothing but the molecular mass of air, right. It is the molecular weight or the molecular mass of air. What is this equal to? 28.97 into 10 to the power minus 3 kg per mole. This is the molecular weight of air, right. G also, you know, it is the acceleration due to gravity. In SI units, this is going to be 9.81 meter per second square. Fine. You are supposed to find out h. R, accordingly you have to substitute R in the relevant equations. So, therefore, in this particular case R is going to be 8.314 in terms of joule, and your molar mass I have said. So, therefore, now equating ln P2 by P1, we have already obtained ln P2 by P1 in this particular case. If you see, this is equals to minus 0.1778. So, we can relate the two, minus 0.1778. This will be equal to this particular portion here. So, we can substitute all the terms here. This is equals to 9.81 into 28.97 into 10 to the power minus 3 into h divided by 8.314 into the temperature 298.15. So, from here what do you get? You get h equals to 1550.8 meters. Well, I'll write it slightly more. This is 1550.8 meters, right. So, therefore, what did you do in this case? In this particular case, basically using Clausius-Clapeyron equation, you found out what should be ln P2 by P1 equals to, right. And then what you did? You performed a force balance here. From the force balance, equating the forces which is acting on this particular infinitesimal volume of air of cross sectional area A and height dH, the forces which are acting on it are the pressure forces which act due to the pressure difference, and this is balanced by the force of gravity on this particular volume element. So, accordingly, from this particular force balance you get this equation, and then the only thing which is given to you connecting dP and V is that the air column or the atmosphere behaves as an it is an under isothermal conditions. So, from there you get this particular equation for relating dP and V. Accordingly, you make the relationships, and from here you get this particular equation. Now, we find you have two equations for ln P2 by P1. One is this equation, one is this equation. Simply equate the two equations and to get H. Now, this was for the first part of the problem. What about the second part? In the second part, it is slightly involved. It is said that the atmosphere, instead of behaving isothermally, it behaves adiabatically, and the gamma is given. So, therefore, in this particular case we find that the relationship between the Clausius-Clapeyron equation, that particular equation, it is applicable in this case, no matter whether the atmosphere behaves under isothermal or adiabatic conditions. So, for part B, definitely we can take up this particular portion, and we can write down for part B ln P2 by P1 equals to minus 0.1778. This we have obtained from Clausius-Clapeyron equation, right. This we already know. Now, for force balance, in the same way that we had done the force balance here, in the same way we can perform the force balance, same approach, and we get this equation as well. So, we write down this equation also. This equation is dP equals to minus GdH by V. The only thing comes that when you want to relate P and V, then in the last problem you had tried to relate them assuming the atmosphere to be isothermal. Now, you will be trying to relate them assuming the atmosphere to be under adiabatic conditions. So, in a previous problem the relationship was P2 V2 equals to P1 V1. In this particular case the relationship is, as you know, it is P1 V1 gamma equals to P2 V2 gamma, right. This is the only equation that you are going to use. This is the only difference from the previous problem, but naturally the calculations become slightly involved in this particular case. So, therefore, if you are proceeding in the same way, we find that in this particular case dP equals to P1 V1 to the power gamma minus gamma V to the power minus gamma plus 1 into dV. Just the same way that we had proceeded in the previous case, we do it, and then we substitute this particular equation in this equation, right. When we just substitute it and then you see what you get. The equation is going to be something of minus gamma P1 V1 to the power gamma V to the power minus gamma plus 1 dV will be equal to minus dH by V, or we can write it down as V to the power minus gamma dV equals to GdH gamma P1 V1 to the power gamma, right. So, you can keep on expanding it, and finally, if when you expand it you find that V2 by V1 to the power 1 minus gamma, this is equal to 1 plus 1 minus gamma by gamma GH by P1 V1. You can again elaborate it further. This V2 by V1 to the power gamma, we can always write it down as P1 by P2 to the power gamma minus 1 by gamma. These are all adiabatic equations. This can be written down then as 1 plus 1 minus gamma by gamma, the same thing that I have written down here, GH by P1 V1, right. So, therefore, from here what do we get? We get from here that P2 by P1, this is simply 1 plus the reciprocal of the thing which I had written down there, GH by P1 V1 whole to the power gamma by gamma minus 1, right. And from there I get ln P2 by P1. I can very well substitute everything here. Now, instead of P, just like I had done in the previous case, instead of P1 V1 I can substitute it with RT1. For 1 mole this is going to be RT1 by M, and therefore, I can from here I can very well write this, I will write later. From here I can very well write this down as P2 by P1 equals to, substituting all the values, we are going to get 1 minus gamma is 0.4 because gamma is 1.4 as it is mentioned. G is equals to 9.81 just like the previous case. Molecular mass is 28.97 into 10 to the power minus 3 into H, this divided by gamma which is 1.4 into R 8.314 into T which is 298.15, the room temperature. So, simply substitute it, and this we know this is ln P2 by, this is P2 by P1, and from Clausius-Clapeyron we had obtained ln P2 by P1 equals to this. From here we get P2 by P1, this is equals to 0.8371. So, I can very well equate this P2 by P1 with the value which I have got here. I can equate both the values. This is equals to 1 minus 3.2755 into 10 to the power minus 5 into h whole to the power 3.5, right. So, from here I get h equals to 1512.3 meters. So, you find in order to find the altitude, it depends upon if the atmosphere is behaving isothermally or if the atmosphere is behaving adiabatically. This portion simply matters when we try to relate the pressure and the specific volume, and for this particular equation it is important to consider the atmosphere in one particular state, but other than that the rest of the problem is same for part 2a and 2b. We need to perform a force balance in order to relate your height with the pressure, and then we need to perform, or rather we need to find out the ratio between the pressures from Clausius-Clapeyron, and equating the Clausius-Clapeyron equation with the force balance equation, where we have made necessary corrections as by considering the atmosphere first as isothermal and then as adiabatic, and after that equating we find out the altitude. So, therefore, this is one particular way by which you can find out the altitude, provided the altitude is high enough to bring about a reasonable difference in the boiling point of water, right. So, now we go to the next problem. We had enough of Clausius-Clapeyron. So, at the moment we would go for some property estimations. Now, in this regard I would like to tell you that we have already discussed property estimations, and we found out that there are several equations, and when we do not know exactly which equation the gas obeys, then under that condition we either refer to the compressibility factor chart or we refer to the reduced coordinate charts which express delta H star and delta S star in terms of a unique function of reduced temperature and pressure. Now, mostly in industries we find that the charts, they are very much used, but since it is difficult for us to provide charts etc. So, therefore, we will be concentrating primarily on finding out these departure functions from equations of state. Now, since for exam purpose using Redlich-Kwong and Peng-Robinson, which is again mostly used in industries, particularly the Redlich-Kwong equation is very much used in the hydrocarbon industries. The procedure is the same, but since the calculations become slightly involved and we are all dealing with hand calculations for the purpose of this class, we would primarily like to keep our problem within simpler equations of state. It can be a van der Waals equation of state, it can be a Berthelot equation of state, which is also a very simple equation of state, or some particular equation of state which is much less involved, just to simplify calculations. But it is important for you to remember that usually in industries we either go for the generalized charts which have been provided by various workers, or usually we use the Redlich-Kwong equation of state. So, if you remember, when I was taking the class, I had derived the expressions for enthalpy and entropy departure functions, right. And I had also mentioned, if you recall, I had also mentioned that these departure functions, they are expressed in the terms of PVT behavior, where you require V to be a function of P. We had found that for most of the equations, the cubic and the virial equations, it is often more useful for us if we can express the functions in terms of P as a function of V and T. So, therefore, we had to make some particular modifications of this equation such that we could express the enthalpy and entropy departure functions in terms of dV instead of dP. I do not know whether you remember this or not, but we had, in order to change these particular expressions, what did we do? V dP is nothing but equals to, we know that V PV equals to RT, right. So, from there we found out V dP, this is nothing but equals to dPV minus PdV. This is true not only for ideal gas, this is true for every gas obeying any particular equation of state. So, instead of V dP, we can make the substitute as dPV minus PdV. What happens then? What are the limits of dPV? When P equals to 0, we know the gas behaves as an ideal gas. So, PV becomes equal to RT under this particular condition, right. So, therefore, we make this following substitution. If we make this following substitution, then instead of V dP, we write it down as dPV minus PdV, right. Now, when we write this as dPV minus integral PdV, fine. The limits are from P equals to 0 to P equals to P. For P equals to 0, we know the gas behaves as an ideal gas. If the gas behaves an ideal gas at P equals to 0, what is the corresponding PV equals to? For an ideal gas, we know PV is nothing but equal to RT for 1 mole of the gas. And for P equals to P, naturally this is going to be PV, right. And we know that for an ideal gas, the volume can be approximated as V infinity or V 0, fine, and the volume here it's V. So, instead of this first term, we can substitute it with the two terms. And then if you recall, we had mentioned that from the cyclic rule, we can write del V del T at constant P. This particular term, we can very well replace it with del P del T at constant V. How? From the cyclic rule, del V del T at constant P into dP at constant T, this can very well be written down, substituted as minus del P del T at constant V into dV at constant T. So, therefore, from the cyclic rule we had gone that. So, therefore, instead of this particular term, we can very well substitute it in this particular fashion. Fine. By doing this, what have we actually achieved? By making these particular substitutions, we find that the equation which we had obtained here, this particular equation, we can write it down. I will just write down the equation once more for your convenience. V minus T del V del T at constant P, whole thing as dP, which can be written down as P equals to 0 to P V dP minus T integral P equals to 0 to P del V del T at constant P dP, right. So, instead of V dP, what do? We substitute it just the way I have written down, we substitute it with PV, and then integration, what does it give? It gives us PV minus RT. So, therefore, from this particular term we get PV minus RT, and for the next substitution, what do we get? It is V equals to infinity to V T del P del T at constant V minus P dV. This is at constant T. Fine, or else we can write it down as in terms of Z. If you want to write RT into Z minus 1 plus integral V equals to infinity to V T del P del T at constant V minus P into dV. So, if you observe this equation, you find that you can find out the enthalpy departure function for any particular equation which expresses P as a function of T and V. Now, let us see what's the problem which was given, the previous problem which we are dealing with. This particular problem, this was to calculate the enthalpy and entropy departure function. For what? For an ethylene gas, right. Now, for this particular ethylene gas, the gas is at 8.25 MPa pressure. So, P is given 8.25 MPa and the temperature is given T, small t is given as 25 degrees centigrade. It is given that the gas obeys van der Waals equation of state. The A of the A and B are not given, you can note it down. It is 453.046 into 10 to the power minus 3 Pascal meter cube per mole whole square. B is 0.057 into 10 to the power minus 3 meter cube per mole. This is given, right. So, once these two are given, then in that case what you need to do just in this particular case, you know that here in this equation you can substitute the for the van der Waals equation. If you see, this is the van der Waals equation. This is the van der Waals equation, and in this particular equation it was a home assignment. If you make this the necessary substitutions here, then in that case the final equation which you arrive at is this. Once you arrive at this equation, you finding out delta H star is no problem. P and V are known, R T are known, A is already given. So, you can find out delta H star, same way you can find out delta S star as well, right. And if you wish a slightly more elaboration on this, on the substitution, then I would like to tell you that, well, P is R T by V minus B minus A by V square. Just to tell you how we arrived at this particular equation. This particular equation from this equation. This was your home assignment. I believe that most of you have done it already. In case you have got stuck up, I will just like to do it once more. P is given, del P del T at constant V is very simple, R by V minus B. So, therefore, delta H star I have already found out, this is PV minus RT. So, P is already given. So, PV minus RT is very simple for you to find out. This is going to be equal to RT into PV by RT minus 1, right. And then if you substitute del P del T at constant V here, then what do you get? You get integral V equals to infinity to V. This is going to be RT by V minus B from here, if you observe, minus again RT by V minus B plus A by V square dV, fine, for V equals to V to infinity. From here what do we get? We get from here RT cancels out. So, you get PV minus RT, and here these two cancels out. So, therefore, minus A by V. You just make the necessary substitutions and you are going to get the answer for this particular equation. The answer for this particular equation is, for this particular equation, P, T, everything is given. So, therefore, for this particular equation, your delta H star, if you make all these substitutions, then in that case I will just make the substitutions for you. First term is PV minus RT minus A by V. What is P equals to? It is given 8.25 megapascal. So, into 10 to the power 6 into 1.1673 into 10 to the power minus 4. This is V. One thing I would like to remind, that this V you have to find out from the basic van der Waals equation. You are required to find out V under this pressure temperature conditions. If you find it out, you find V to be equals to 1.673 into 10 to the power minus 4. It might happen that in some problems, just to reduce the calculation time and all, we might be providing you the volume, but normally under conditions you are supposed to find out the specific volume, right. Minus RT. What is minus RT? R in this case is 8.314, T is 298.15 minus A by V. A is already given, 453.046 into 10 to the power minus 3 divided by 1.1673 into 10 to the power minus 4, right. Make the calculations, you find that the delta H star, which is nothing but the actual value H minus the ideal gas value, this is going to be minus 5.397 kilojoules per mole. Make the calculation and find it out for yourself. In the same way, you are supposed to proceed for S minus S0. This also, if you recall, this part also we had derived. Again here we have del V del T at constant P dP. Substitute it with this and we have R by P dP, right. So, therefore, in this case also you can substitute it. If you make the necessary substitutions, then what do you get? Once you make the necessary substitutions, I will just write it down once more. Your delta S star then becomes equal to, in this case it is minus del V del T at constant P integral P equals to 0 to P minus R by P dP at constant T, fine. So, this if you make the substitution, you get V equals to infinity to V del P del T at constant V dV plus R dP by P integral P equals to 0 to P. How to make this? This is already substituted. So, you have V equals to infinity to V del P del T at constant V dV. For this case, what do you write? For this case, you write integral dPV by PV. You simply write down the equation and then you make the you just write it down and divide and by V. You get this as R integral dPV by PV minus dV by V, right. Here again you are going to put the limits. What are the limits? This is RT to PV. What are the limits for this? V equals to infinity to V. So, what do you get finally? Finally, the thing which you get is R ln PV by RT, which is again nothing but Z. This particular thing is nothing but Z. So, you can also write it down as R ln Z plus you get V equals to infinity to V integral del P del T at constant V minus R by V. I will just write it down, integral V equals to infinity to V, this is dV, this is dV, isn't it? I have taken this term out and I have combined these two terms because both of them are in terms of dV. So, therefore, what do I get here? This is R ln Z plus integral V equals to infinity to V del P del T at constant V minus R by V dV, which gives me, on slightly little more substitution, it gives me R ln Z plus R ln, if you observe in this particular case here we get dV by V. So, R ln V minus V by V infinity minus V minus R ln V by V infinity. Agreed? So, therefore, from here you can make the substitutions, or in other words you can also write it down as R ln Z, slightly more substitution, V minus B by V infinity minus B minus R ln Z RT by P into P0 by RT. Can you not do it? Because V infinity is the ideal gas volume, right? V is Z RT by P. I have just made some substitutions. So, therefore, this gives me as R ln, because R ln Z they are going to cancel out, and finally what I get, R ln V by B by V minus B plus R ln P by P0. Agreed? Which is nothing but R ln P into V minus B by P0 into V infinity minus B. Or in other words, this is nothing but R ln P into V minus B by RT, isn't it? So, therefore, you find delta S star comes from a very simple equation. Again, if you refer to the previous problem which was there, if you go to the previous problem, you find that in this particular equation, you know R. What is R? 8.314. ln P, you already know 8.25 into 10 to the power 6, right? V minus B, fine. This is 1.1673 into 10 to the power minus 4 minus B 0.057 into 10 to the power minus 3 divided by R 8.314 into 298.15. You can find it, this is nothing but minus 13.431 joules per mole Kelvin. Please try it out for yourself and see if you can get this particular equation or not, right. So, this is, we have found out enthalpy and entropy departure functions. We have assumed that it obeys the van der Waals equation of state. So, therefore, we have expressed it in terms of from a pressure to a volume explicit form, that is, we have expressed it as P as a function of V and T. We have used that equation and we have found out the enthalpy and entropy departure functions. Now, suppose it is not a van der Waals equation of state. Suppose I say that, well, it obeys some other equation of state, which is not a van der Waals equation of state, but it is more or less, it shows that instead of A by V square, there is also a temperature term there, quite expectedly, because intermolecular force of attraction depends on the temperature as well, right. So, for this case, just proceeding in the similar manner, can we not find out the delta H star and the delta S star, the enthalpy and entropy departure functions, just the way we have done it for the van der Waals equation of state? We start in the same particular manner. This is our basic equations. This and this are our basic equations. We make this and this substitutions just the way we had done for the van der Waals equation, and then what do we get? We get delta H star equals to RT into Z minus 1, just the same equation I am writing down, infinity to V T del P del T at V minus P into dV, just the equation we had obtained. This can be written down as PV minus RT, as you know, plus integral V equals to infinity to V. This is 2A. If you make the necessary substitutions, then in that case, if you write the Berthelot equation, I will just go to the equation once more for you to see it. If you go to this particular equation, what does it give you? It gives you P equals to RT by V minus B minus A by TV square, right. So, therefore, and then from here you can also find out what is del P del T at constant V. This is nothing but equals to R by V minus B, right. So, therefore, we can very well substitute that whatever we have obtained, and so therefore, here in this particular case, what do we get? We get this as 2A by TV square dV, fine, and then this becomes equals to PV minus RT minus 2A by TV, which gives you RTV by V minus B minus A by TV minus RT minus 2A by TV. On further simplification, we get BRT by V minus B minus 3A by TV. You can compare this with the van der Waals expression that we had obtained. in the same way you can proceed for in order to find out the entropy departure function as well. In the entropy departure function also, again I start with the same equation which I had derived, right. Equation was R ln z plus v equals to infinity to v del p del t at constant v minus r by v constant t dv, which can be written down as, in this particular case if you substitute all these things, you get v equals to infinity to v, we get r by v minus b minus a by t square v square minus r by v into dv, right. So, here for what do we get? We get r ln z plus r ln v minus b by v infinity minus b minus r ln v by v infinity minus a by t square v, which can further be substituted as plus r ln, with all the simplifications you get v minus b by v minus a t square v. Right. So, therefore, if you know, or rather if you can express your enthalpy and entropy departure function, then in that case whatever be the equation of state, you can substitute it, and accordingly we can you can find out the enthalpy and entropy departure functions for any particular cubic equation of state. The same is true for the van der Waals equation of state as well. If you do not know whether the gas obeys any particular equation of state, then definitely we have to resort to the generalized charts to find out the enthalpy and entropy departure functions. So, this completes our assignment, or rather our tutorial for the 4th week. I would welcome much more questions for you, so that for the tutorial of the next week we can include all those doubts and we can address whatever concerns you have. Thank you very much.